Okay, this is integrated 2, 7.2.1. Now we're going to continue on with probability, but we're going to move to conditional probability and what independence means. So conditional probability is when you know one event has already occurred. So if the event has already occurred, what's the probability of a separate event occurring now? So that's what we say with our conditional here. So we've got our notation of conditional probability. Basically, that is probability of B given A. So B given A. That's what that vertical line is basically telling you. So given. So B given A. So the thing is, we know the second event has already occurred. That's what we're trying to figure out, the probability of the first one now happening because of that. Okay, so looking at this, we do have a formula for this. So the probability of B given A, and then I'll use the formula, but I'm also going to do it a different way too, because I like giving you a variety of ways to look at this. So this is the same thing as the probability of A and B. So that's the intersection, like what we talked about in the last notes, over probability of A. So now it's important to note, I'm going to go ahead and bring this over here too so we can take a look at the notation. Probability of B given A. A couple things that might help you figure out what goes where inside the formulas. So if we take a look at who comes second, so what's already happened. So we already know after the vertical bar has occurred. So if we take a look, the A is after the vertical bar. Whatever comes after the vertical bar is the probability that goes in the bottom of this thing. That's important to know. Then the top of it, it doesn't matter if it is A intersect B or B intersect A. The order does not matter, but the top of it is the probability of them both occurring simultaneously. But I do think it's kind of nice to know though, the given part, that's the probability that goes on the bottom. Okay, independence. We're going to talk about independence and associated, and they are not the same thing. They would be opposites of each other. So independent events are events that do not affect each other. It's important to know. So if the probability of event A has absolutely zero bearing on the probability of event B, then we would say that they are independent. One way to actually test that is to check the formula. Probability of B is equal to probability of B given A. Now, we can actually manipulate this a little bit, so to find maybe a way to kind of wrap our brains around this a little bit easier. So I am just going to ignore the left-hand side for the moment, and I'm going to use the formula for the probability of B given A. So I know that what has definitely occurred is A. So the probability of A is going to go on the bottom. Remember, it came second, so it goes on the bottom. The top is going to be the intersection of the two. So probability of B intersect A. So I used the formula to rewrite the right-hand side. Now I'm just going to drop the left-hand side down. Okay, that doesn't look better yet, but it can. I'm going to go ahead and treat this, because these are just numbers, I'm going to treat these like a fraction is equal to a fraction. So I'm going to put a 1 underneath the denominator of the probability of B. And then I'm going to cross multiply. So that would give me the probability of B times the probability of A is equal to the probability of B intersect A. Okay, this is another way to check this. If this statement is true, then we know that B and A are independent events. So if true, B and A are independent events. So that's another way to do it. Or you can go and use the original problem. Probability of B is equal to the probability of B given A. Another way to check it. Okay, So here we have our example. This is the example directly from your notes. So take a moment, pause the video, read through the question so we're all on the same page, and then we can proceed. Okay, so taking a look at this data, what we have here is a two-way table. It is not an area model at all. This is just identifying and organizing some information that's given to us. So for example, if we take a look at this and I look at this number 72 that I've circled, all it represents is that from shift 3, 72 of the items that were produced on that shift would be classified as satisfactory. That's it. That's all it is. Just a way for us to kind of organize the data. You can also see that there are totals in here. So if I take a look at the 5 that I've circled in red, this is telling me this is the total of the defective column. So out of all of them that were produced, 496, out of all of them that were produced, 5 of them were defective. That's all that's saying. So now that we have a better idea of how to maneuver our way around this table, let's go ahead and take a look at these questions. Find the probability the tire chosen at random was produced by shift 1. Okay, so I'm going to say probability of shift 1, and I'm going to look at the table. So I'm going to find all of them for shift 1, and the total was 231. So I'm going to put that on top. So 231 total created from shift 1. But then I have to think about how many were made completely. Shift 1, shift 2, shift 3, if there was an A shift or a B shift, all of them. That's going to be the bottom right-hand corner, 496. So I'm going to put that in the bottom. So probability that it was created by or produced by shift 1 is 231 over 496. Okay, let's get rid of those marks. And we'll go to the next question. All right, find the probability that a defective tire was produced by shift 1. Okay, this has a lot going on. So I did reword it for you. That is, we want to find the probability that it was shift 1 given that the tire is defective. So what we know is that the tire is defective. We already know that. So if I write this out, probability of, okay, the given part is that it's defective. I know for sure it's defective. Now, what is the probability that it came from shift 1? So that's the first part here. All right, so if we go through and we use our formula on this, a couple of ways to do this. We can do the probability. So remember, we want the probability of the second event is going to go on the bottom. Oh, got a tight little spot here. So on the bottom, I'm going to put the probability of defective. Since I know that has happened, it's definitely defective. On top is going to be the intersection between shift 1 and defective. So I look at my table. Well, the probability of defective, all right, that's the total. So defective probability is going to be, there's a total of 5 of them out of 496. But of those 5, so I'm not even going to look at the 496. I'm going to consider 5 as my entire sample space because I only care about it being defective. So there out of all of them, there were 5 that were defective. Out of those 5 only, how many came from shift 1? Well, that was 1. So it's going to be 1/5. Again, not the only way to do it, but that is one way to do it. Okay, so then let's take a look at the next one here. And this is us trying to determine if things are independent or not. Now, if they are independent, then we know that relationship. So back on the previous slide, our formula, probability of B is equal to probability of B given A has already occurred. Or we could do the probability of B times the probability of A is equal to the probability of A and B. So we do it a couple of different ways. Now, if they are the same number, then yes, it is independent. If they are not the same number, then we say that they are associated. So if we take a look at this, there are so many different tire conditions in this problem. So my recommendation to you is to just pick one. So if I take a look at this, let's do perfect. So I could do probability of perfect. So I'm going to let that be my event B. Okay, now I want to think about, so independent of shift. All right, pick a shift. So I think I'm going to do shift 1. So it's going to be probability of perfect given shift 1. Okay, now when I set this up, so how do I know which ones I'm supposed to do in what order? You want to make sure that the probability of whatever event you have over here is the one that comes first in the given situation. For sure, you don't want it second. That doesn't help you out here. So now we're going to go through and we're going to do the math. So if we take a look at this, probability of perfect. Well, there were 210 that were perfect out of a total of 496. I'm wondering if that's equal to, okay, so remember, this is going to be the probability of shift 1 goes on the bottom because we know it's already happened. So probability of shift 1. Okay, shift 1 is 231. So 231 is going to go on the bottom. Now, just in that row, which one of those were perfect? Well, of those, I think it was 106 were perfect. So let's put 106 on top. At this point, we're going to type those into our calculator and see if we get the exact same decimal on each side. So when I typed on the left-hand side, I got 0.4233. I don't know if I'm going to put a mark through that equal sign or if I'm good with it. So I'm just going to leave it there for now. And then when I typed in the right-hand side, I got a 0.4588. That's not equal. Put a slash through that thing. My explanation for this is my work that goes with this. So I would say that tire condition and shift are not independent. Okay, and I have another example for you on this one because conditional probability can be a little tricky the first time. So see if you can figure this one out. You'll notice that the totals are missing, so you're going to have to fill some totals into your table. See if you can answer these questions. So pause, do it yourself, and then check your work against mine. Okay, so double check your work against mine. And then notice the question on part C was asking if they are associated. You're being asked to perform the exact same calculations as if you're trying to determine if they are independent. So if the two fractions are 100% equivalent to each other, then yes, they are independent. If they are not 100% equivalent to each other, then we say that they are associated.